So let's start off from where we ended last time, and we will finish the chapter today. I think we ended with creating the replay buffers for the corresponding observers after we created the DQ and environment. Uh, then we needed to create the training matrix, and then yeah. So let's start from here. Chat.
So which section was it? The creating the DQN agent? Was that where we're starting, or where is it?
Yep, we had created a training matrix too. We had created a replay buffer for the corresponding observer, which had the 1 billion trajectory. Then we used the 2015 DQN paper with a frame stack 4 to construct that. And we had a custom class that we had show progress. Then we can start from creating training metrics, or we can back it down a bit. Because
okay, creating training metrics. Okay.
yeah.
Let's see. Creating the replay. Anybody object if we go back to creating the DQN agent? That's like 2 sections back. Start with that. Okay, and then the rest of the chapter is, I don't know, can we do that? Yeah. Well, we only have this session, so let's do what you originally said. Let's start with creating the training metrics, because that's page 655, and then we'll have a chance of getting to the end.
Yep.
Okay. Yeah. Okay. So,
or else we will have to do this.
We don't have time in the schedule for another session on this chapter.
Yeah.
Okay. So what time will we reconvene? It's roughly 6:40 now. 7:30.
After 40 minutes. Yeah, I will
40,
start a time.
40 minutes. Okay, 40 minutes. Okay.
Hey guys. You guys listening to Clubhouse or what?
Sorry, what was the question?
So do you guys listen to Clubhouse?
Oh, yet another very popular social network to spend and waste all our time.
Uh,
I
yep.
haven't. I'm on Clubhouse. I haven't been using it.
Okay. Cool, because since last week it has uh, uh, how do I say it? It has improved with respect to the quality of the uh, uh, conversations, and even with respect to you can talk about AI. There are paper on reading sessions by Karpati, Justin Johnson. So yeah, uh, that uh, helps. Uh, all the there as in Twitter, there is an academic Twitter and research Twitter and the practitioners with respect to the machine learning part. So they also have their own groups that are being reconvened to that they have clustered, and it kind of helps uh, from uh, gathering the latest research, talking to those folks, hearing their thoughts, and even Musk is there. So, uh, yeah.
Yeah, Musk was one of the first ones to
Mm,
really sort of publicize it. At least
mm,
that's when I start to hear it.
yep.
Following you, Mayank.
Hmm. So, let's start with the reading. I think so. Everyone must have finished it. Let's read it. So, last time, I think so. Everybody must have managed to uh, run this. Terence had some problems with running this on Colab. Uh, I couldn't look into that. The Terence, what was your uh, uh, evaluation of the notebook there?
I put a couple of the notes in for some of the items that I found, but I ran into issues right after that execution. So, and I haven't had a chance to look at it again, but when I can, I'll get back to it and I'll
Hmm.
post it in the chat.
Okay, no issues then. You must be able to run it on the current machine also that you have. Uh,
No, I don't have a GPU machine. So I try to do everything I can on Colab.
but it will also fall back to the CPU, no? if you try to
Yeah, it's just
set.
slower. It's just
It's
slower.
extreme. It would be
Yeah, it's
extremely slow.
extremely
Yeah,
slow.
on the CPU.
Yeah,
It is.
yeah.
But I may end up doing that. That way I can run it for as long as it needs to.
Mhm.
So that's probably the next thing I'll do if I
Yeah.
can't get through Colab.
Okay, good. Uh, sounds interesting. Maybe we should also tweet that this on the author. Uh, read him into, because he is updating all the notebooks with respect to the updated TensorFlow and the Scikit versions that come out, and maybe we can uh, loop him into. I will try to I will try to map that request that Joseph has raised in on the GitHub. Yeah, maybe ask that query to him too.
Great. Thank you.
Yeah. Okay, so let's now start. So we have created the DQN agent last time. Uh, it was just a bunch of disparate classes that we had to combine together in a particular way. And this was a DQN agent. Uh, uh, and we discussed this last time with respect to the laws, the discount factors, the environment, the action specs. And since it was a breakout game, and so the actions were four, the four actions that was being mapped by the dense layer. Yep, get action mapping. Nope, fire left, right, and left that were being mapped. And we plotted these observations. Yep, this was the direction in which it was heading. I'm just giving a quick recap of the ball. Then we created this DQ and agent with respect to these parameters, three conv layers. Uh, on the Q network class, we looked at the construction of this Q network class, the source code, and what parameters are required. Then the DQN agent, the replay buffer, and these hyperparameters that were taken from the 2015 DQN paper. Then this is a show progress kind of a metric that counts and displays the number of times it is called. This is with respect to uh, uh, kind of uh, hmm, uh, a form of evaluation of this. Uh, so we can interpret it on the basis of those metrics that we are running. And show progress class was used as a this is the simple log metric, and these are the TF matrices that were there. Uh, we will come back to it, show progress when we have utilized it in our class here. And yeah, I was talking about these four: number of episodes and environmental steps, average return metric, and the average episode length metric. This will give us the insights into the how much time and the uh, number of with respect to the number of episodes, the number of steps, the most average of the average return per episode and the average episode length. I think so. If everybody is comfortable with this, quite easy. And then we created a collection driver, a collect driver, uh, with respect to uh, passing the current time steps to the policy, choose an action, and returns an action step object containing that action. So it's a wrapper around the uh, uh, basic action, and then the driver is then passes the action to the environment, which returns the next time step. And finally, the driver creates a trajectory object to represent this transition and broadcasts it to all of observers. So this is the broadcasting with respect to updating uh, those transitions. Yeah. Uh, uh, and this is a stateful policy since those actions are chosen both on the given time step and their own internal state. So at each time step, that agent has uh, full information uh, of the current state that it is in. Um, then those driver is a kind of a wrapper that handles that, as we have alluded to earlier. Then mm, plus also the driver saves the policy to the trajectory in a policy info field. You have the policy info field. This is with respect to the dynamic step driver class, and these are the four attributes that they do with respect to collecting the policy, the replay buffer observer as we have defined it here, plus the train metrics and the update period here. Last time I mentioned uh, uh, last time we also had a discussion about the holistic view of how those uh, uh, mm, intuitive concepts are represented, but this time we will go through the dynamic step driver and the dynamic episode driver class to see how it's actually implemented in the code. So uh, here, as we have seen, the batch time step uh, driver on the first case, as I was alluding to, the A environment may be the batched A environment in which the driver passes a batch time step to the policy, then which is a time step object that contains a batch of observation, a batch of step types, a batch of rewards, and a batch of discounts. Um, these are the batches. These are all the batch of same size, and then driver also passes a batches of previous policy states, and then uh, this kind of whole data structure can be combined into a, uh batch trajectory with respect to uh, this batch trajectory containing all those things. We club it all together and send it in a object. And then these are the dynamic. So this was the conceptual understanding of how it works with respect to that architectural data flow inside the how do I say it? Those steps, actions, and policies And yeah, with respect to those blocks of information that needs to be configured to work in a sensible fashion. And then we have this dynamic step driver, which we use, and as we have used those matrices from the 2015 Nature paper. So those train matrices that we defined earlier, these are the train matrices, the replay buffer observer. Yeah, this is the replay buffer. This is the replay buffer observer with respect to that TF uniform replay buffer class. And these guys here. The update period with respect to the number of steps that it has to take. I think so. This was 4. Yep, 4, since the running a training step is every 4 collection steps. At each 4 collection steps, mm, update period is there to evaluate the velocity of the ball. Then we create the data set. Data set is with respect to collecting those batch of trajectories, and then we try to sample them based on the method that we have used, based on that sample at epsilon greedy policy. I think, or in DQN. I think so. They have used a prioritize. So that was in the rainbow paper. You will see what have they used to sample it. Then this is the buffer info object that we get from the trajectories buffer replay buffer next. These are the fields with respect to those trajectories. Let me policy. These are the 2 episodes that are taken here. These are the fields. Step type, observations, actions, policy info, next step type, rewards, and discount. This is the trajectory buffer info combo that we get from this guy here. This is trajectory fields. If you look at the trajectory, yep, this contains the action, discount, next step type, observation, reward, step type, and these are the main parameters here of this trajectories class, and we are using this fields underscore fields. These are the protected attribute. Yep, that we use. Protected attribute underscore field to give a representation here. The buffer info. Let's take a look at the buffer info. What it contains. Buffer info. Yep. So it contains the ID, the probabilities. Protected attributes are the field defaults and the fields. These IDs are with respect to those tensors. And the probabilities with respect to them. Okay. So this is with respect to the replay buffer.get next. Since we are sampling the batch size of 2 and a number of steps that we have taken as 3. each containing the 3 consecutive steps. So this is the example of what they're doing here. Movement for object that contains the sample identifiers and sample identifiers and the sampling probabilities. As we have looked at this, these are the IDs and top probabilities. So this identifiers, the sample identifiers are with respect to two. Since we have taken sample batch size of two, this 0 and 1 represents the sample batches that are taken from the trajectory. And those probabilities are represented as this. The shape is 2, and we have two top probabilities here. So, and the number of steps that they have taken is 3. So therefore, the each tensor has a shape of 2, 3. Yet, I think so this represents, if I'm not mistaken, yep, I'm not. This it seems like I will take a look at this in detail and update if you know it of the trajectory here. Okay. And then currently moving forward, these are the fields 1, 2, 3, 4, 5, 6. Trajectories dot observation dot shape uh, with respect to 2, 3, 84, 84, 4. 84, 84 is the size of the image, and 4 is the number of steps. I think so. 2 is the uh, number of batch sizes, and 3 is the number of steps. So this is the tensor that we have. Let me trajectory.observation.steps. Observation. View this. So that's the tensor that we get. Okay, this is currently a sparse tensor. Then we have converted the steps type to NumPy and displayed it. This. So it represents this guy here. Here in the notebook, they have also decomposed the trajectories into time steps, action steps, and next time steps. So you can take a look at these 3 too. So, what? So these are the time steps.
We seem to have lost our leader.
Zach? Yeah. Sorry, guys. This got disconnected. Uh, me. I think we were in the middle of, I guess, exploration versus exploitation trade-off came to a. Mm, no. Where we were trying to, yeah, give an idea of the trajectories here with respect to those step types, observations, that decomposition into the fields. These are the protected fields. These are the collection of the protected fields that are there. And, yeah, we try to see them. And here they have given a much broader interpretation of the same. Mm, yeah. Let's take a look at this figure. That's intriguing to see at each time step. Each field contains a tensor whose first two dimensions are 2 and 3, and there are two trajectories, each within 3 steps, as I've alluded to. This is the shape of the observation. Uh, there's two trajectories, each with 3 steps, and each step observation is 84 cross 84 cross 4. Yeah. Similarly, the step tensor has a shape of 2 cross 2.3. Both trajectories contain the 3 consecutive steps in the middle of the episode. In the second trajectory, we can clearly see the ball because it disappears in the next 2 observations, as we can see here. The agent is about to lose a life, but the episode will not end immediately because it still has several lives left. So if you can see the score here, 1, 1, 1. This is the first trajectory. This is the second trajectory with 3 steps. Here the agent has scored 5 points. Or it may be the, yeah. It's not the score. I think so. The left one represents the score. The middle is, I don't know. I'm not sure about the middle and the. right part. There are some matrices you can say, and yeah, if you're playing this game, it matters. But here we are taking a look at the observations with respect to how to formulate those problems. Mm, Then we take a look at the trajectory as a since each trajectory is a concise representation of a sequence of consecutive time steps and action steps, which is designed to avoid redundancy. Uh, this is this guy here. Uh, if let's take a look at the figure 18.16. Mm, Here the trajectory step n is the reward. Trajectory step n plus 1. The trajectory step n also includes the next step n uh, equals step type n plus 1. It's the basic stack of how they are put together. Uh, it's a batch in which they are stacked together, so you can see them as a combination of those six um, um, uh, attributes that we looked at earlier and how they are stacked in a uh, mm, trajectory object. And yeah, and those trajectory objects are stacked together to form mm, here a queue or simple stack here. This is under, as we have looked at, this is under what's the name of the wrapper? Mm, The time step, and within that time step, if we take a look at the class time step, we might get a idea as to what data type they have used here. This is the time step class, PF agent trajectories. So the name tuple, step type, reverse discount observation. Yep, so in here we can uh, have look, this is a simple tensor, but which data type have they put it put together? Specs tensor or array? Okay. Yeah, I will have to take a look into this very detailed understanding of what the union here represents, the spec tensor and array. Uh, nested. This is the nested spec tensor or array. Okay, okay. So this is simply a how do I say it? A representation of those uh, step types in an array like this guy here, and uh, the second type here represents the nested spec tensor or array here represents the nested sub tensors with respect to those nested sub variables or data types that can be used inside a class. So if naively you can think of it as if you have a dictionary and the key value pair, and if the value is a combination of list, so top at the top level those dictionary types can be submerged with those lists, and those lists can also be submerged with a simple string type or something like that. So this is the hierarchical representation. I think so. Everyone is already comfortable with this, and then intuitively, what they have here shown is uh, simply those step types which go from n to n plus 3, and the discount factor that we had, and those transitions. For the audience that are present here, it's very much easy to digest it, and uh, it's a kind of a simple recursion if we can take a look from that perspective too. But here, I think so they have applied a simple loop from n to nt plus 1 steps with the rewards and discount factors. I think so. Everybody is comfortable with this. Or do you guys have any questions here? Okay. Then we have the sample trajectory that may overlap 2 or more episodes. Yep. Uh, that will have a kind of a boundary transitions where with the step type equal to 2 and the next step type equal to 0. Uh, why is this the case? Uh, because at the boundary condition we may get a, a trajectory whose discount factor with respect to those since the discount factor is at the end step of the discount factor is the lowest if we take a look from t to t plus n. So, uh, uh, so to handle that trajectories, that those boundary transitions come into play. This, of course, is described in a much detailed uh, representation in a much detailed factor for if we look at the form DPs, that is the partially observable MDPs. There, these transitions, as I have alluded to earlier, they come into play for the type of the environment which they are in with respect to those hidden observations. Uh, uh, formulating those formulating or sampling those trajectories uh, help in uh, calculating the optimal probability transitions across the batches of trajectories that we can use from. So, uh, like in the game Montezuma's Revenge, we have seen earlier that last state may have a complete negative impact, but when we are resetting the policy, when encountering a boundary condition, uh, those edge cases are handled in those, how do I say it, uh, much more mm, optimal way. Yeah, you can simply put it with respect to the optimality of those conditions. I'm currently lost for words for how exactly those form MDPs are being uh, 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 represented with respect to those trajectories. But yeah, if you can search for that form DPs and why those boundary conditions actually matter. In that case, it's very much self-explanatory to it. So, yeah. And it's a very big problem in the case of reinforcement learning. So it has been detailed multiple times. Then we go on to the next. This was a tangent with respect to one of the problems that I faced while training my agents. Now let's go to the main training loop. Instead of calling the get next method, we are using a TF data sets. And this is the power of the data API, prefetching and parallelism. We looked at it quite a few times earlier. So this is the prefetch 364 trajectories and 3 parallel number of parallel calls. It equals 3 and the prefetch here is 3. So prefetches with respect to those 3 batches. We have already looked at this in chapter, I think so. Yeah, 13 with respect to the loading and pre-processing data with parent support. Then here we have this. Here the author represents a note saying that if the for on-policy algorithms, such each experience should be sampled once using from training and then discarded. In this case, you can still use a replay buffer, but instead of using dataset, you would call the replay buffer gather all method for each training iteration to get a tensor containing all the trajectories recorded so far. And then use them to perform a training step and finally clear the replay buffer by calling its clear method. So this is with respect to this algorithm. Yeah, what should we do here? It's an alternative way, but yeah. Then we have all the data sets and the batches in play. And then we call the training loop. But first we have collected this imported function, which wraps this with some extra experimental options to convert it into a TensorFlow functions for better performance. And this is the collect driver run function and the agent.train function where we looked at this. This is from the TF agent. Then we can run the loop. Just run collect driver.run and the agent.train method is called here. Yep, this is the run here, which we have just converted. It's a wrapper. And then this is the train. Yep. So if you look at it, this is simply a agent.collection.get initial state, and then the iterator on the data set, and then we are looped it, then decompose this run into time steps and policy states. From the next iterator, we get the trajectories and the buffer. And then from these trajectories, we get the training loss, numpy. And then for each of the 1,000 iterations, we log the training matrices. Yeah. It's the same that we have defined here on this paragraph. And since, yeah, then, yeah, this is the end result that we get. And here we have iterated it for 10,000 steps. This agent will keep on improving. After I ran this, I had this for these number of steps, the 10,000, I get a loss of 0.123, 0.4 times 0.02. That's 1e minus 4. Oh, or will it be 1e minus 5? No, it will be 1e minus 5. That is this. Then this is the for each 1,000. I think so. We have logged it, and you can see the um, absolute value with respect to those mapping of the structures, team agents. This is the at the iterations at the team logs, numpy and the end. So this is the number of episodes. These are the matrices that we have. The gradual progression we can see here. Other than this, here we can see the number of episode lengths that are firstly 174. The average number of episodes is 23. The environment step is this guy, and it's constantly increasing. The average return is 1, then it's 0.5, then 0.5, 1, 1, then 1.7, 1.4, and 0.8. And the average episode length is this guy here, this guy, and this guy. Then how do we visualize it? This is with respect to this prompting. The watch driver, with respect to the progress that they have seen here. And you can see the breakdown here. See the path. This is yeah. 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 So you can see here. This is the presentation. The gift that we created. Okay, so let's go ahead. Yeah. Yep. This is with respect to since we have trained it, and these are the matrices that we have seen, and this is this. Okay, now there are some extra materials with respect to DQs versus rotating lists, and uh, for the larger replay memories, then uh, uh, how much time will this take as respect to DQs here? And then we have the timed episodic uh, we calculated the total time that it will take for the number of runs. So yeah, I think so. This is the standard deviation with the 7 runs. Uh, uh, this many loops, and yeah, we have created this. Then alternatively, we can create a operating list like a replay memory class for much faster access to large replay memories. And this is with respect to uh, the replay memory that they have created, a custom replay memory. Also, there are a couple of additions. If we look at TFA agents, I will discuss them in the end. That have recently been done and the time it with respect to the mem samples here. Then creating, so this is the improvement that we see. Then they have created a custom TF agent environment here, which extends the Pi environment class. This is the extension. I think so. This is not given in the book. Yep. So if we need to create this, the author has given us sample of those overriding functions that we can use from the Pi in environment, that the action spec, the observation spec, and underscore reset, the underscore step protected methods that are there. Yeah, overriding them. This is how a TF agent does it. Then this is a simple time step with respect to those in environment, and this guy here is the first step that we take here. It is wrapped around the time step class. So these are the extra materials with respect to the performance improvements and the custom TF agent environment that we can create. So that's this. Any queries about until now? Good. So let's take a look at overview of some popular RL algorithms. Now we're transitioning to the theory perspective. The actor critic algorithms. What are they? This actor critic algorithms. Let me share those slides in the chat as well. This is by Sergey Levine. This is the best resource that I could find with respect to explaining the family of actor critic that combines the policy gradients with the deep Q networks. So policy gradients, reinforcement algorithms that we looked at just now. And the actor critic contains two neural networks, a policy net and a DQN. So this is an example of a policy gradient. This is the gradients that are summed up across this by the rewards of the state action pairs. And then, yeah, these parameters are updated. This is the improvement to the policy steps that generates the samples. Then improving the policy gradient. So we can see from this green dot here, we can have these many trajectories, and we sum together those rewards to get a kind of best possible estimate of the next T steps. So that's what is being done here. That's what in this that's what is in this slide. It's just a mathematical formulation of how do we sum together these rewards to get an optimal that's closer to the optimal. Then here is about the baseline. How do we evaluate it? Then this is the state and action value functions. With respect to generating the samples, creating a model to estimate the return and improving the policies. This is the value function. It's the same, but when we apply this to a deep neural network, what are we had the value of that policy parameters. Then we evaluate those policies with respect to this function approximations that are applied together. And then can we do better? And then this is the policy evaluation example. This is also referred to as the Bootstrap Estimator. So this has been applied in the TTCAM, I think. So we looked at this game 2, this research paper by Gerald and AlphaGo. So this is the value function and how is it being done. Then we come across to the actor critic algorithm. First we fit this to the sample reward sum, and then we evaluate the action from this guy here, the next state minus the current. So this negative value iteration reduces the variance of the actions that we need. Yeah, so this is the evaluation step here, and the value function that we get, and this is the loss. which we can take a look at with respect to those feature space. If I represents the feature space. And then these are the discounts and policy gradients. Yeah, won't go into the mathematics of this, but because this will require some time. This is without discount and online actor critic, in which it is continuously updated. So I think you guys get this. And then there are multiple additions with respect to what can be done here. Uh, uh, let's not go into this much detail. Uh, okay, so basically we got to know what an actor critic agent is, which contains the two neural networks, the PolicyNet and the DQN. The DQN was trained by the experience, and the PolicyNet uh, is much faster than the regular policy gradient approach. And the since the action value estimates is relied on the DQN that is calculated by the critic, so it's much faster. Here it's a perfect summation. In on the last line, it's the actor critic algorithm is bit like an athlete, the agent learning with the help of a coach, the DQN. This is a very good formulation of how the actor and the critic is there. You can intuitively evaluate it. Then we have to take a look at the asynchronous advantage actor critic, or AC3. Here, asynchronous. So yeah, this is the asynchronous method. Yeah, we specifically take a look at this algorithm, asynchronous advantage actor critic. So here, what we are doing is all those steps that we have seen for the actor critic, it's just being done parallelly with respect to learning from the multiple agents. Like in AlphaGo, they uh, applied a variation of this uh, to beat the Go player on Lee Sodol was his name, if I'm not mistaken. And why is it asynchronous? Because we have to explore different copies of the environment in parallel, and each agent then pushes some weight updates to a master network. Master network here will be a kind of a you can say a pattern like a master slave, where the master will have multiple slaves there with respect to n number of parallel environments that are being uh, evaluated based on that particular uh, time step and action of a previous uh, agent, and then it pulls the last. Then each agent contributes to improving the master network from what the other agents have learned. And since this is a simple asynchronous way, and folks that are familiar with uh, are here are already kind of familiar with how this works and how the estimation of an advantage of each action, which is uh, uh, bounded by a upper and a lower parameters, but it also gives rise to some sort of a generality with respect to those policy and value functions. And then those estimates of that DQN at every action is calculated, which stabilizes the training. So if you look at the mathematical formulation of how the intuition works, this guy, A S comma A uh, theta comma theta V is an estimate of an advantage function given by this guy, which we looked at earlier, and then which is upper bounded by the T max, as I've said. Uh, the pseudocode is represented with this guy, and the value function, the value-based methods are rely on the parallel actor learners and accumulated updates for improving training stability. And then we get this. The convolution neural network has a soft max output for the policy this guy, the value function. Then they have uh, improved their convergence with respect to that policy by adding an entropy function. And then gradients, the full function, including the entropy regularized term, is written as this guy here. And the hyperparameter beta here contains controls the strength of the entropy regularization term. So this is the asynchronous advantage active critic, which they are. And the algorithm, I think so. They have the pseudocode is presented here. Yes, this is the pseudocode. This is how it's done. This yeah, I think it is in the appendix part of this chapter 23. You can take a look at that. This is algorithm S3. Mm, yeah, this is, uh, okay, and then let's go forward for the advantage actor critic. A2C algorithm. This is a variant where it removes the asynchronicity. Uh, uh, all updates are synchronous, so gradient updates are performed over larger batches, which allows the models to better utilize the power of a GPU. So for a GPU, this is required. Uh, they can add advantage of those larger VRAMs available in a GPU. So yeah, we can do this. Then this is with respect to, and then we come at the soft actor critic, the SK3. This was proposed in 2018 by UC Berkeley researchers. Here also it maximizes. We are using some entropy term to maximize it. There's also a very good article here with respect to explanation of this particular algorithm in the Berkeley AI lab, which they improved, which they implemented, sorry. There are some two figures too, with respect to rotating a valve with a dexterous hand and learning directly from that raw pixels, stacking Legos. This is a main Tor robot. These are the deep RL using this software to detect in the real world environment. Look at this. And this is the entropy augmented objective that we have here. This is the data of how this is how this works. And let's see, try to show you the this is the main algorithm. With a JPy, yeah, JPy of this pi is here, is taken from here. So we can take a look at the research paper in much detail, and then we can get a formulation here with respect to those spherical Gaussians of how they are implemented intuitively. That's very much interesting. Since since I am already uh, off time, I've already overshot. I will just quickly try to give an overview of the remaining two algorithms too. This is the proximal policy optimization and the curiosity-based exploration. Uh, Guys, if you have any queries, please free to interject and ask away. The proximal policy optimizations were introduced by OpenAI. And this had a clipped surrogate objective, which was a simplification of the previous TRPO. So the main objective is this guy here. And this second term, we have the expectation of the minimum of the first term and the second term here. The second term modifies the surrogate objective. This is the objective that we had by clipping the probability ratio, which removes the incentive of moving the rewards outside the interval, 1 minus epsilon and 1 plus epsilon. So it is bounded. This is the plot of the one time step that is being shown here. This is the optimization with respect to those red circles. Yeah. So this is from a high level view of what it's doing. This algorithm is also available in the TF agents as well as SAC and some others too, DQN, as we have seen earlier. let's now quickly take a look at the surrogate objectives that interpolate between the initial policy and the updated policy parameters after the one iteration of PPO. So, yeah, this is it. This is the L CPI and the expectations of the clip, which is clip between the 1 minus epsilon and the 1 plus epsilon. Yeah, so this is the linear interpolation factor and how this improved. There were other methodologies also that were elevated here with respect to the adaptive scale divergence, the fixed scale, and all with respect to those D-target parameters at 0.003, 0.01, 0.03, and this beta parameters for the fixed scale part. But the clipping with respect to this performed the best with epsilon 0.2. This is from the control benchmark over 21 runs of algorithms on 7 environments. This was a proximal policy optimization, and we also have a cool representation here. This is an agent that's running towards the ball. Reach the target, the pink sphere, which learning to walk, run, and turn using the momentum here. Yeah, you can take a look at this too. Two little complicated robots. This. And this guy here. So yeah, you can play with this, and yeah. Also, they have released an update for the GPU implementation for the PPO2. Yeah, but there are many different flavors of the active critic. With they have also released a flavor with experienced replay, sample efficient policy gradient algorithm. This is a cool read too. We should go to the curiosity-based exploration. That's very good. If we look at the recurrent problem of RL in the sparsity of rewards, which makes learning very slow and inefficient. Here, sparsity refers to the goals. Let me try to map a problem from the curiosity-based exploration point of view. So this is the map scenario. S is the starting state, and the star is the goal. And what is the aspect of sparsity in these environments? So here we have room 17 that is very sparse, room 13 that is sparse, and if our agent gets around here, then it's dense. So here we have three formulations as to the categorization of those sparse fixed locations. So they are being categorized into these three forms. And then this is the dense reward settings, the sparse reward settings, and the very sparse reward settings, and how these AC3 algorithms are being have been training in these uh, these rewards with respect to these rewards. So any queries here? I think so. It's very much similar, and we have discussed this earlier too, with respect to how these rewards will affect those properties and how those rewards will affect those convergence factors with respect to uh, the hardness of exploration tasks that we have with respect to the distance and the goals that go from dense to sparse rewards to very sparse rewards. So, yeah, please free to ask. I'm already 15 minutes over time, so I don't want to take much of your time, but this is cool. This is curiosity-driven exploration, and much of the, as I have alluded to in the exploration of environments with respect to those corridors and rooms. So this I didn't had this research paper earlier. I didn't look at it earlier, so I couldn't give a intuitive explanation of why this works. So you can see exploration versus this is what curiosity brings to the table. Um, any queries? And this is from the, yeah, this has already been given here. This paper. Hmm. Hey guys, can you hear me?
Yeah.
Yeah. Uh, yeah. On NeurIPS, there were, I think, 3-4 papers that I looked at in RL that use curiosity in some form or the other. So it's a very much how do I say it? Popular technique that is being used nowadays for adapting our policy to maximize some sort of a reward. It's a basic technique that is being implemented across many papers. So.
Okay, well, let's wrap up and since you got through it all.
Yeah.
And
I
thank
think
you so
so.
much.
Here they have played also with Super Mario. Yeah, they have given an example of Super Mario here in the paper, in which using the curiosity-driven explorations, it was able to make significant uh, progress for the level. This is a simple intrinsic curiosity module of the state and the feature vectors and the diagrams that they have implemented. Oh, thanks. Thank you all. I can keep blabbering for I don't know, a couple of hours more on these topics. So it's not a problem for me.
Yeah, it's good to wrap up though, because we're 20 minutes over. So
Yeah.
yeah. So thanks so much, Mayank, for getting through this last bit. Actually, it was more than a bit. It was quite a lot. And taking us through the whole chapter on RL. And I guess we're probably all of us here looking forward to the RL course that's going to start in a few weeks.
Yeah, for sure.
Months, yeah.
Cool. So let's meet on Sunday with chapter 19.
Yeah, Alvaro is going to lead us in that one.
Yeah.
All right.
Thank you,
guys,
Mayank.
Yeah, thank you.
Thank you.
Yeah, thank you. And we'll see you all on Sunday. Bye-bye.
Bye. Thank you.